Welcome back to our series on multivariable calculus. In this episode, we're going to talk about vector integrals, in particular doing surface integrals with the vector surfaces we just learned how to draw in the last episode. Recall that we can already do an integral to find surface area. That was defined in the last video. And those, of course, look like this. We were going to do some integral over some sort of surface of r of u crossed with r of v. Take the magnitude of that, du dv. Well, we've already done surface integrals up to this point. We did them in terms of functions in 2 dimensions. So this simply represents something we've already looked at before. When we did that, of course, we did a dA area. And of course, we can do that here too. Except I don't want to necessarily call this dA because dA looks like we're going in terms of the dimensions the function's written on. We tended to do 2-dimensional integrals for surfaces dA. But this isn't a function of u and v. U and v are actually the vector parameters that draw the function. The function's still in terms of x, y, and z. So the new name we're going to give this is the integral over d of ds, where we'll use s as a capital S. ds is going to then sort of represent what dr represented for us before. In other words, all of our integrals, the line integrals that were dr represented sort of the differential of the r parameter for the space curve. In this case, ds represents the 2 partial differentials of r, ru crossed rf. The magnitude of that du dv is all included inside ds. So from now on, when you see that capital ds, know that unpacking it is far more complex than just a dA. dA would represent probably differentials within the dimensions that we're integrating by. It might include the Jacobian if we're doing a conversion into another system of measurement. But in this case, the ds really implies much, much more. It's these little parallelogram areas that we're going to integrate over the surface in terms of the parameters u and v. Well, let's see some different things then that we can do with this integral of ds. We could certainly do a functional integral, just like we did when we did line integration. We wanted to use the line as just a parameter that fixed some aspect of the function. So the function covered space, we were only interested in integrating it along the space curve. Well, in this case, the same thing can apply. We can have a broader function and we only want to integrate it just over the area defined by this ds. So we could do that. We could do a double integral over d of some sort of f of x, y, ds. And the ds would imply that we've got some sort of outside surface that's being parameterized for us that's limiting our integral of f of x, y. Of course, in order to do this, because this will still be an integral in terms of the parameters u and v, we would have to replace x and y in the function we're integrating with those parametrics as well. So that's one aspect of it. Of course, if f of x, y is just 1, then it becomes a surface area. The surface area would just be the double integral of 1 ds. And then we can consider some other things that we did with surfaces and volumes. We found center of masses by finding mass functions and then the functions of the various different moments. We can do a similar thing with any surface that we can parameterize. That is, I could find the mass by simply taking the double integral over d of the density function. And of course, that would be expressed in terms of some x and y coordinates ds. Same thing, I'll have to replace the sigma function with my parameters for x and y as u and v, but this would give me the mass. And then I could go ahead and find m of xy by throwing the z coordinate in there, sigma xy ds, and then I could find the z coordinate of the center of mass by taking the ratio of the moment for x and y to the mass itself. And I could do the same for the y and the z directions. The key here is we're going to operate on the premise that because ds already represents our surface integral with our parametric, that we're going to have to use those substitutions for every other function that comes in. So we can find surface area with this new ds integral. We can integrate over any function and we can apply it to our center of mass evaluation. In essence, where we talked about doing line integration before, this whole class is sort of referred to as surface integration and is very much in parallel with the line integrals that we did to open this unit.